Now there are a lot of real world problems which are solved using graphs. Okay, so if we want to solve the problems in graph through our programs, then we need some kind of mechanism to actually read what is the data present in the graph, or to search some data which is present in the graph. Okay, so as a two operations, one is reading all the data which is present in the graph, and second operation was searching some data in the graph. Okay, now if you want to read all the data which is present in the graph, this operation is called as a traversing. Okay, and searching is actually just searching, right? So to perform these two operations, we are having two mechanisms. One is depth first search, and second one is breadth first search. Okay, now this depth first search works simply as a pre-order traversal of a tree. Okay, but we cannot apply pre-order traversal on graphs. Okay, for example, if assume that you are having this graph, this is node A, this is node B, this is node C, this is node D, right? So this is some graph, and graphs can also have cycles, right? Now assume we are trying to perform a pre-order on this graph, pre-order search. So what is this pre-order? Pre-order is root, left and right. Okay, that means initially you are going to visit the root, then you are going to visit the left subtree, and then you are going to visit the right subtree. Okay, now assume you are trying to apply this pre-order in this graph, and we started from this vertex A. So this vertex A is actually the root, right? So if this vertex A is root, so initially we are going to print A, then we are going to print the left subtree and the right subtree. So assume here B is the left subtree. So when B is the left subtree, therefore in the left subtree, this B becomes a root in the subtree, right? For this B, we are having this D, right? And we are having this A. So for this B, this D can be some root, some left subtree, and this A can be right subtree, right? Because there's no way of knowing that for any node which one is the root, and which one is the left subtree and which one is the right subtree, right? Because in a graph, a node may be having 20, 30, 40 different nodes attached to it. If you are trying to apply pre-order, then you may stuck in infinite loop, and you are going to print the same data which you have already printed before multiple number of times, right? Therefore we cannot apply pre-order, we cannot apply post-order, we cannot apply in order, we cannot apply double order, and even we cannot apply triple order, right? Because in all these cases, for any graph, those kind of operations are not successful, because those operations may lead you to the infinite loop. Okay, so we need some different kind of mechanism where we have to identify that what are the nodes which we have already visited, and what are the nodes which we haven't visited as yet. Okay, that means we will be visiting those nodes in future, right? And we need to document all these things. Plus there should be proper mechanism to do all these operations, right? So for these operations, the first mechanism is depth first search, and the second mechanism is breadth first search. Okay, now let us see what is the depth first search and what is the breadth first search. So here in the case of depth first search and breadth first search, we can write a program, but the simpler way is we should write an algorithms for this depth first search and the breadth first search, because in that way it will be much easier to understand. And plus in exams, in depth first search and breadth first search, they do not ask you any program, they just give you some graphs and they tell you that please find the depth first search and breadth first search of this graph, or they may ask you what is the time complexity of depth first search, breadth first search, etc. Okay, but they are not going to ask you any program for depth first search and breadth first search, because it is not asked till this point of time. Okay, so in depth first search, before applying depth first search, we should know how the graph is stored. Okay, for example, we are having this graph. This is node A, this is node B, this is node C, this is node D, and this is node E. Okay, and here in this case, A is connected to C, A is connected to B, B is connected to D, D is connected to E, C is connected to B, and C is connected to D. So assume that we are having this given graph. Okay, and for this graph, so what is the adjacency list representation, or what is the adjacency matrix representation? So if you try to give a adjacency list representation, so in that case we'll be having a list like this, right? And this list may contain some pointers, okay, right? So by the way, you can easily create a structure for this list. So what is the structure? We can do struct, so give some name, let us suppose node, and it is taking character data and node star pointer. Okay, and this is struct node star pointer. So this is the node of this for this adjacency list representation, right? In the adjacency list representation, we are having this following array. Okay, and in this array we are having two parts. This part is the data part, and this part is the pointer part. Okay, we can simply define an array of this size. For example, how to do it? We just do struct node data, or you can give some name, assume that this graph is G1. Okay, we can do struct node G1 with 5 index locations. Okay, because in this graph we are having 5 nodes. So what will happen here is there will be an array and this array is going to have 5 index locations. What are the index locations? This is 0, 1, 2, 3, 4. And in this array there will be a data part and there will be a pointer part, right? And this data part is going to contain the node, the name of the node. For example, this 0 is containing A, 1 is containing B, 2 is containing C, 3 is containing D, and 4 is containing E. And this is the pointer part, and this pointer part is going to point to some node. Okay, and what are those nodes? These are the nodes which are adjacent to this vertex A. And here the nodes which are adjacent to vertex B. Here the nodes which are adjacent to vertex C. Here the nodes which are adjacent to vertex D, and here the nodes which are adjacent to vertex E. Okay. Now for the vertex A, what are the nodes which are adjacent to vertex A? The nodes are B and C. So assume this is the node B, and the second node is C, and this is storing null here, right? For B, what are the adjacent vertices? Adjacent vertices are A, C, and D. So it is going to point to the node A, second node will be C, and third node will be D. Okay, and here the order doesn't matter. It may happen that C may come before A and A may come after D, and anything can happen because order does not matter in this kind of linked list. Okay. Now next is the node C. For the node C, the adjacent vertices are A, B, and D. So these are A, second vertex is B, and third vertex is D. Okay, for this node D, the adjacent vertices are E, C, and B, which are E, C, and B. Okay, and for this node E, the adjacent vertex is only D. Okay, so this is the adjacency list representation for this graph. Okay, and now let me just write the depth first search algorithm, and then we'll see how we can apply depth first search algorithm on this graph. Okay, and remember, this depth first search algorithm uses stack, and the breadth first search algorithm uses queues. Okay, so the depth first search algorithm goes something like this. DFS on a given vertex, we start from a given vertex. For example, the vertex is U, then we have to make visited of U is equal to 1, and then for each vertex W, which is adjacent to we are going to do this following operation, and the operation is if this visited of W is equal to 0, then we are going to do DFS of W. Okay, so this is a very simple form of a depth first search algorithm. Okay, there are a lot of different forms of depth first search algorithms are available in the books. In some books they're using colors to identify which nodes are visited, which nodes are not visited. For example, in you say the Tenenbaum book and in Narasimha Karumanchi book, in both these books they are using a gray color to note that we have just arrived at a particular node, and they're using some different colors, for example a white color or a black color, to identify between three kinds of nodes. Okay, three different things on node. So one operation can be when a node is inserted onto the stack, so then they are going to change some color, maybe the color is gray, and then when a node is already visited, then they are going to change the color, then maybe a black, and so on. So they are using different colors notations. Okay, so what we are going to do is to identify that the nodes which we have already visited, we are going to maintain an array, and this array will be a visited array. Okay, so what will be the array like this? This array will be like this. Okay, this array name is visited. Okay, and every index location is actually denoting one node. So I can use something like this also, right? And here this index location is denoting node A, this index location is denoting node B, this index location is denoting node C, this was denoting D, and this is denoting A. So initially for all these index locations, the visited value is 0, right? So what is this visited value as 0? So whenever a node is not visited, we are going to say that it is not visited, and it will be denoted by 0. And whenever a node is visited, then we are going to make this visited value as 1. So if the visited value is 1, therefore we are going to just we are going to say that this node is visited now, and we are not going to visit this node. Okay, so let us come back to this DFS algorithm and let us see what will happen in this DFS algorithm. Okay, so in this algorithm, as obviously we are using a recursive call here, so what will happen is, let us try to create a recursive tree for this. So DFS of U, so this U is denoting the node where the node from which we have started. For example, here in this graph we can start from the node A. Okay, so if we start from the node A, then we are going to call DFS of A. So okay, so when we are calling DFS of A, so initially in this DFS of A, we are going to make the visited array for this A as 1. So that means we are going to go to this visited this one, and we are going to make it as 1. So as you can see in this algorithm also, the first line is to make the visited of this particular node as 1. Okay, and then the next line is for each vertex which is adjacent to this vertex U, we are going to say if the vertex is not visited, then apply the DFS algorithm to make it visited. Okay, so let me just show this with the graph, with this stack. So initially we called DFS of A. Okay, so when we called DFS of A, right, in that case it is not going to print anything, right, because I have not applied any printf statement here, but we can apply a printf statement after this DFS call or before this DFS call, doesn't matter. Okay, so this will matter somewhat, but you have to see that you want to print the data before this or after this. So ideally it is this printf statement will come after this DFS call. Okay, so what will happen is we are going to call DFS of A. So when we call DFS of A, in that case we are going to make visited of A as 1. Then we are going to see what are the vertex which are adjacent to A. So how we are going to see that? We are going to use this adjacency matrix to identify what are the vertices which are adjacent to A. So in this case, the vertex B and the vertex C both are adjacent to A, right? When both these vertices are adjacent to A, I will just pick one vertex and I am going to apply DFS on that, right? So here what I am going to do is I am going to pick this vertex B and I am going to apply DFS on B. So because this visited value of B is not 1, therefore we are going to call DFS on B. Okay, so when we call DFS on B, right, so remember that DFS of A is already into the stack. We haven't removed it because we haven't finished this complete execution, the complete program for DFS of A. So we are going to we'll go to this DFS of B, and then we are going to apply this depth first search on this node B. So when we apply depth first search in node B, so what is the first operation? So first operation is to make the visited value as 1. Okay, and then the second operation is for each vertex W which is adjacent to this vertex B, we have, if it is not visited, then we have to visit it, right? So in this case, you see the first vertex is A, and the visited value for this vertex A is already 1. Therefore, in that case, this if condition will be failed. So we'll again try to execute this same for loop, and then we are going to apply the same for loop into this vertex C, right? And in this vertex C, if you see the visited value is not 1. It is 0, it is not 1. So therefore this C is not visited. So we are going to call DFS on this vertex C. So when we call DFS on this vertex C, so first thing which we are going to do is we are going to make the visited value as 1, right? And then we are going to go to all the adjacent vertices which are adjacent to C, and then we are going to apply this DFS algorithm in all those vertices, right? But in the case of C, you can see there's a vertex A. This vertex A, the visited value for this vertex A is already 1. We are having this vertex B adjacent to C. The visited value of vertex B is already 1. So we are having this vertex D which is not visited as yet. So we are going to call DFS on vertex D. So when we call DFS on vertex D, in that case, we are going to make this visited value as 1, right? And then we are going to see what are the vertices which are adjacent to D. Okay, so the vertices which are adjacent to D are E, C and B, right? So in this case, the first vertex is E, right? Therefore, and we are going to see the visited value for this E. The visited value is 0, therefore this E is not visited, so we are going to call DFS on this E. So when we call DFS on this E, so the first operation is make this visited value as 1, and then we are going to see what are the vertices adjacent to E. So the vertices which are adjacent to E is D, and you can see in the visited table that D is already visited. So this program will finish for E, therefore this E will come out of this loop, this stack, right? And if we have a printf statement after this DFS statement, or for you say a printf statement here, not there actually. So if we are having a printf statement here for this E, then we can say that we are going to print this E, right? And then we'll go back to the previous call. In this D, we are going to see what are the other vertices of D. So what are the other vertices here? The vertex are C, and the second vertex is B. So but for this C and B, the visited value is already 1. So therefore the DFS of B is finished. So we'll go back to the previous statement, and we are going to print D, and then we are going to call DFS of C. So when we call DFS of C, in that case, this front, we have already visited A, we have already visited B, and we have already visited D. Therefore, this DFS of C will not be executed, right? Actually, it will be executed because it is already executed, but the thing is, it has finished all its recursive calls, right? Therefore, we'll come back to the previous statement here. So it is going to print C here, and then we are going to check this DFS of B. For this B, we have already visited A, we have already visited C, and we have already visited D. Therefore, the call for this B is finished. So we'll come back to the previous statement, and then we are going to say C for this DFS of A. For this DFS of A, we have already visited the this node C. So we have finished all this recursive call. Therefore, it will also come out of this stack. Therefore, we are going to print A. Okay, so this will be depth first search, or you can say, right, you can say it as depth first search for this given graph. Okay, now as you can find, for a given graph, there may be multiple different depth first, right? And it depends on your adjacency list. So in the case of your adjacency list, if a node comes before this, for example, here B comes before A, therefore initially we are going to call this B, and then we are going to call the A and so on. So the node which comes before the other node, so it depends on them that which on which node we are going to call depth first search now, right? So let us see an animation on this depth first search, and let us see how this depth first search is working, right? So I guess you have got some kind of idea from this, and after this animation I guess it will be clear to you, right? Now in this website, go to the graph algorithms. In the graphs algorithm, check the depth first search algorithm. Now in this depth first search, as you can see, they are maintaining two arrays. So one is visited and second one is parent. So let me just make this diagram as undirected. So we are having this graph, and here visited value for all these nodes are initially false, right? So if the video is not clear, then I'm telling you that visited value initially is false. So it may look like 1, but it is actually false, okay? And let us see the adjacency list representation for this given graph. So this is the adjacency list representation, and this is the logical representation, and this is the adjacency matrix representation for this given graph. Okay. Now let us see. We start from the vertex 0. So when we start from the vertex 0, so in that case we are going to make the visited value of this vertex 0 as true, and then we are going to visit all the adjacent vertices. So if you see this call, then it is calling it all this adjacent vertices. So just check the list representation from this, and then you get some idea. So how they are working. Right. Therefore, the call for 6 is finished. So we'll go to the previous call, which is DFS of 1. In the DFS of 1, the first node was 5. So we are going to visit this node number 5, and then we are going to see what are the nodes which are not visited. So how we are going to see which are not visited? By using this visited table. Right, visited array. In the visited array, if the value is t, that means it is already visited. If the value is f, that means the node is not visited. Okay, so let us see for some of the other graph. Assume that we are having this graph. So do one thing, draw this graph into your notebook, and let me just tell you these nodes, or let me just try to make it zoom for you. Right, so I guess this much is enough. Okay, so these vertices are 0, 4, 2, 1, 6, 5, 3 and 7. Okay, draw this graph in your notebook, and then keep this graph with yourself. When you are watching this, it's DFS on adjacency list representation. Okay, then this will help you understand from which node we are going to go to which node. Okay, so I'm just playing this adjacency list representation. So let us just start the DFS from the node 0. So remember, we are making a recursive call on different nodes. So whenever we are going to make a recursive call, the control will pass to that particular node. So DFS of that particular node. Okay. right? So we have already done this thing. So check this graph. So check the order of visits here. Okay. We can also use this adjacency list representation. From this adjacency list representation, we can make a recursive calls. For example, we are at row 0. Row 0 is representing that node number 0. For this node number 0, there's only one node which is adjacent to this, which is the node number 4. That is why this value is 1 here. Then we will go to this node number 4, and for this node number 4 we have already visited node number 0. In that, if we start from 0, then we are going to call this node number 2 and so on. So let's just watch this complete video. If I start from 0, the row number 0, and let us see how this matrix representation is working. Right, so we finished this representation. So if you see the logical graph, this was the order of DFS calls. Okay, so now as you can see, to find the DFS and BFS of a graph, we haven't studied BFS as yet, but if we are going to study the depth first search, in that case also we do not actually need the diagrammatic representation of the graph. So we have any of this representation, that is the diagrammatic representation or the linked list representation or the adjacency matrix representation. Linked list means this adjacency list representation. Okay, if we are having any of this representation of the graph, then we can simply find the DFS of that particular graph, right? That means we just have to identify what are the nodes which are adjacent to the node on which we have called depth first search, and then we have to explore all the nodes which are adjacent to this node, and all these nodes we have to apply depth first search recursively. Okay, now let us see this implementation, this adjacency list matrix representation actually in working. So assume we are having a graph, and this is the adjacency matrix for that graph. Okay, I'm not actually drawing the graph, I'm just saying that we are having this adjacency matrix. And the nodes in the graph are A, B, C and D. So this is A, B, C and D. So assume that there is a node between A to C, there is a node between B to A, there is a node between B to D, there is a node between C to B to C, there is no node, therefore C to B there will not be any node. Okay, B to A there is a node, so A to B there must be a node, right? And C to B there is no node, so therefore A to C there is a node. Okay, and then we can have a node between make it, let's say D to B, or we can make a node between D to C, right? So there's a node between B to D, right? So this can be 1 and others are 0. So assume we are having this graph. Okay, a graph can be directed or undirected, so it doesn't matter. Even if the graph is directed, you do not have to see the complete diagrammatic representation of the graph. You can just use the adjacency list and adjacency matrix to identify which are the nodes which are actually adjacent to any particular node, and we can apply DFS or BFS on that particular node. Okay, so it is not necessary that you can apply this DFS or BFS only in undirected graph. You can apply it in directed graph. How you're going to do it? You're just going to see what is the adjacency matrix representation, or what is the adjacency list representation, or even you can use a diagrammatic representation, right? And for every node which is adjacent to a particular node, call the same DFS again. Okay, so for example, here in this case, if we are having this array, and this array is storing what are the nodes which are visited. Okay, so here the nodes are A, B, C and D, and initially all these nodes are 0, because that means none of the nodes are visited. So if we start from this vertex A, the initially we are going to make this vertex A as visited, and then we are going to encounter the first vertex which is B, and we are going to make this B as visited, and then the control will transfer to this B, because we are going to make a recursive call for this B, and the first is this A, and this is already visited, so we'll check the other node which is adjacent to B. So the other node is D, therefore make a recursive call for D, and we are going to make it as 1. Then we'll come back to this D, and in this D we see that there's a node between D to B, and this B is already visited, so the control will go back to the previous statement. Now in this statement you can see that there's no node which is adjacent to B and not visited, so all the calls are finished. For this B, the control will go back to the previous statement which is A. In the A, we are going to explore the second adjacent node to this A, which is C. Therefore the control will go back to this C, and in this C you can find out there is only one node which is adjacent to C, and this node is already visited, so we are going to make the C as visited, and the control will go back to the previous statement. And in this statement we have to see is there any node is it visited or not. Okay, and then we can print these nodes like this only. Okay, now the previous algorithm which we have done was depth first search algorithm, and in the case of depth first search algorithm, if you are having any graph, then it is not necessary that you are going to visit all the nodes which are present in that graph. Okay, for example, if you are having this graph, the graph is A, B, C, D, this is node E, this is node F, this is node G. So this A to B is connected, B to C is connected, and then D to G is connected, D to F is connected, F to G is connected, and there's maybe so these are the connected nodes, right? Now if you apply this depth first search on this A, then you can only visit the nodes which are adjacent to A. That means which are for which there's a path which is existing, not actually adjacent, because when we say adjacent, that means there's a direct node between A to that particular node, right? And when I'm saying there's a path, that means we can have multiple number of nodes if we try to reach from this source node to the destination node, right? For here example, from A to C, there's a path which is existing. So if for any nodes, any 2, 3 or 4, any number of nodes are there, and there's a path which is existing, there's a path which is connected to those two nodes, then we can find a DFS to that node, and from this DFS we can reach all the nodes which are connected to this starting source node. Okay, but the nodes which are not connected to this source node, we cannot visit them. For example, if we try to apply DFS on this A, then we cannot reach the node E, we cannot reach the node F, we cannot reach the node G, and we cannot reach the node D. Okay, now if we apply DFS on this node D, so if we apply DFS on this node D, then we cannot reach to the node E, we cannot reach to the node A, we cannot reach to the node B, and we cannot reach to the node C. We can only reach to the node G and F, right? So in case of depth first search, it is important that the nodes should be connected, and if the nodes are not connected, then we are not going to search the complete graph, right? For that we can use a depth first traversal. So what is a depth first traversal? Depth first traversal looks something like this. So it is DFT, and this depth first traversal is going to take the graph and the number of nodes in the graph. Then for each node, for I is equal to 1 to n, that means for each node in the graph, make visited of those nodes at 0, right? And then for I is equal to 1 to n, that means for each node, if the node is not visited, if visited of that node is not equal to 1, then you can apply depth first search on that particular node. Okay, this can be an algorithm to apply depth first traversal. So as you can see, there's a difference between a depth first search and there's a difference between a depth first traversal. In the case of depth first traversal, we can visit all the nodes present in the graph, right? We are going to traverse all the nodes which are present in the graph. But in case of depth first search, we can only visit the nodes to which there's a path existing from the source node. Okay. Now try to apply this depth first traversal on this graph. So if we apply depth first traversal on this graph, assume that we are not having this ABCD, we are having the node numbers are 1, 2, 3, 4, 5, 6, 7 and so on. So initially we are going to make a visited of all these nodes as 0. So then we will start from this node and then we are going to apply depth first search on the nodes on this node A, and if you apply the depth first search on this node A, then we are going to visit the node B and we are going to visit the node C, and then this control will pass to the previous function to this depth first traversal, and then we are going to apply this in this D. For this D, we are going to visit all the nodes which are for which there is a path existing from D, and then we are going to, the control will go back to this DFT, and then we are going to apply this depth first search on this node E, and by this manner we can visit all the nodes present in the graph. Okay, so do one thing. This is the algorithm for depth first traversal. Try to apply this algorithm on any given graph. Okay, take some demo graphs, 5, 6, 7 different graphs, and try to apply depth first search on those graphs, and try to apply depth first traversal on those graphs, and try to make those graphs as directed. Take some graph which are undirected, take some graph which are not connected, take some graph which are already connected. Okay, and try to apply all these both this depth first search and depth first traversal. Okay, now let us see some of the previous year gate questions on this depth first search and the depth first traversal. Okay.